Welcome to CEC lectures. Myself, Dr. Preeti Jagwani from Department of Computer Science, Arabic College, University of Delhi. So presently we are going through a topic of memory management, and to be precise, we were looking into a dynamic storage allocation problem in which the concern was how to satisfy the request of n processes from a list of free holes. So we have a list of free holes from where we need to allocate the memory, and what could all be the possible techniques through which this memory can be allocated. And we were going through the techniques and solutions to this problem, or what are the various available techniques are the first fit, best fit and the worst fit, and we have already seen the first fit strategy, and we have also seen that that's not the kind of perfect strategy in terms of utilization of memory, because it results in a lot of space wastage. So here we will begin with the best fit strategy. Now best fit, as the name indicates, that the smallest hole that is big enough is going to be allocated to a particular process. And now in order to find this smallest hole, one must search the entire list unless the list is ordered by size. So if the list is ordered by size, we can say the task becomes easier. Otherwise the search will go through till the entire list is going to be finished, because we are actually looking for the best fit. That means the smallest hole that could allocate a particular process, and it produces the smallest leftover holes. That is one of the we can say advantage. In order to understand this process, let us take a look at this figure. Now let's say I have a process size of, let's say, 40 units or 40 MB, and here is the list which is available here. And now here you can see that list is not we can say not ordered by its size, so the entire list has to be searched. While if you can recall, in the first fit allocation it was not the case. The moment you are going to have one large enough hole to accommodate the process, the search ends. Here the search is not going to end unless you have looked into the complete list. So for 40, if we look into the block 1, the block 1 is kind of, yes, it can occupy this 40, but it is very huge. It is it is resulting in a memory wastage of 60 units. Then come to the second block, which is 50. Yes, it could be another possibility, because the size which we are looking for is 40. So 50 could be one of the possibility, having a kind of wastage, we can say, of 10 units. Next block, which is block 3 of 30 units, is not at all a possibility, because you cannot accommodate your process here. Then we have a block 4 of 120, and in this case it is going to waste 80 units of memory. And the last option, which is of 35 units, which is block 5, is not an option to be considered, because it is not the kind of the hole which is large enough to accommodate a process size of 40 units. So now three choices are available. One is 100, one is block 1 of 100, another one is block 2 of 50 units, and the third one is of block 4 of 120 units. So among this, if we look into the memory wastage thing, the best possibility which we are having is block 2, which is of size 50. So in that we are having a 10 units of wastage, but this is the best fit which can be taken. So this is what your best fit strategy is. You need to look through the whole availability of the holes, and then in that situation it is to be kind of given to the hole which is giving the minimum wastage, or which is the best fit. So after this first fit and best fit, we have the third strategy, which is known as the worst fit. Now worst fit says allocate the largest hole. It is also like the first fit. In this, the worst fit also, the entire list has to be searched unless it is sorted by size. this strategy produces the largest leftover hole. This is kind of one very important point which is to be considered here. The first fit strategy was also producing the leftover holes, but the best fit strategy was producing the smallest leftover hole. Now, the idea behind producing this largest leftover hole, or why should one be using this worst fit, is this largest leftover hole may be more useful than the smallest leftover holes from a best fit approach, if you can say. So, that is one kind of we can say motivation behind using the worst fit strategy. Now, in order to understand this worst fit strategy, let us take an example. So, the similar example having of process size 40 and the availability of block 1, block 2 till block 5 is of 100, 50, 30, 120 and 35. So, similarly, as we have seen in the the best fit, the worst fit is also going to scan through the whole list, which is having size of 100, 50, 30, 120 and 35. So, there are three holes we can say which are eligible in order to hold this process size of 40 units. One is block 1, another one is block 2 and third one is block 3. Now, if you can see, block 1 will result in a space wastage of 60 units, block 2 will result in a space wastage of 10 units, while block 4 is going to result in a space wastage of 80 units. So, this is the worst in terms of utilization of space or utilization of memory, and the strategy which we are looking for or which we are considering is also looking for the worst fit allocation or the worst fit hole. So, this process of the process size 40 will be allocated will be given this block 4, in which the leftover space or the hole which is left over will be of 80 units. So, this is the worst fit strategy as we have seen earlier. We have seen two strategies, one is the best fit, another one is the first fit, and here we have also seen the worst fit allocation in the problem of memory allocation. And now, in dynamic storage allocation, we have seen these concerns, or we have seen these techniques of best fit, worst fit and these strategies. Now, coming to these comparisons of these three strategies, we have the both first fit and the best fits are better than the worst fit in terms of decreasing time and storage utilization. Obviously, storage utilization is better in first fit and it is the best in the best fit. Neither the first fit nor the best fit is clearly better than the other in terms of storage utilization, but we can say first fit is generally faster, because we are going to allocate the first hole which is available and is good enough to hold the process. So, the first fit we can say is generally faster. Now, all these are basically policy decisions that how to allocate the memory. Now, with this let us kind of open one more topic of fragmentation. So, now what is happening here is, whenever a hole is being allocated to a memory. Now, let us say for example, we try to recall that example of the best fit, in which we have given a block number 2 of 50 units of memory and the process requirement was of 40 units of memory. Now, what is happening here? The 40 units of memory is taken by the your process, while the 10 units are wasted. That means, now here is a fragment of the memory which is being which is kind of we can say unused as of now. Now, this gives the problem of, or this opens the door for a new discussion which is which is being named as fragmentation. Fragmentation, basically we can say it is a problem, it is an unwanted problem in which the processes are loaded and unloaded from the memory and the free memory space is fragmented, as I have just presented an example. And these processes cannot be assigned to the memory blocks due to their small size, and memory blocks will be staying unused. So, for example, we are going through the continuous memory allocation, and that continuous memory allocation is going to allocate space to the processes whenever the processes are going to enter into our memory, into our random access memory. Now, this random access memory or the memory space are divided either by the fixed partitioning or by the dynamic partition, that these two techniques we have already seen. Now, but what is happening, whether it is a fixed partitioning technique or it is a dynamic partitioning technique, the process or the task which is continuously going on here is loading and unloading of the processes from the memory. Now, what is happening here? As the processes are being loaded and unloaded from the memory, these areas are fragmented into small pieces of memory that cannot be allocated to the coming process. So, for example, process block 1 has leftover memory of, let us say, 10 MB. Similarly, block 3 is also having a leftover memory of 10 MB, but these 10 MB but these two fragments of 10 MB each are available at the scattered places or at the scattered location. Now, let us say there comes a process which is looking for a whole of, let us say, 15 MB. Can we allocate this 15 MB from whatever we available? Ideally, we must, but the situation says 10 MB is available on one location, another 10 MB is available on another location, and these are not merged. So, that means there are two fragments of the memory which are kind of able to satisfy the need of a particular process collectively or in the merged form, but unfortunately they are not merged, and hence these memory blocks stay unused. So, whenever these processes are being loaded and deleted from the memory, they generate some free spaces, and these free spaces we can say are holes in the memory, and these holes or these fragments are available in in the form of small blocks that cannot be allocated into to the new arriving processes, and hence the memory is being kind of used inefficiently. Now, why these processes, why these blocks cannot be allocated to the upcoming processes? Because of their size, and that is the cause. Main memory is available, but it is insufficient to load another processes. Because of dynamic allocation of main memory processes, we have memory, but that memory is actually scattered at various places, and this is what the cause of this what we call is the fragmentation. So, fragmentation is an unwanted problem, or actually it is a concern in which the memory holes are available at scattered processes, and these holes are left empty because they are small they are small enough so that they cannot fulfill the requirement or the memory requirement of the upcoming new processes. Now, coming to the types of fragmentation, one is the internal fragmentation, another type of fragmentation is in external fragmentation. Now, let us try to understand them one by one. So, internal fragmentation says when a process is allocated a memory block, and if the process is smaller than the amount of memory requested, a free space is created in the given memory block, and due to this the free space of the memory block is unused, which causes internal fragmentation. So, in case of internal fragmentation, we can take the similar example as we have taken earlier, that there is a process of size 40 and the best fit is going to give us a block of size 50. Now within that size of 50 block, 40 units are being occupied by the process, but 10 units are being wasted. That means there is an internal fragment of 10 units which is being created here, and that is actually unused. Or similarly we can look into another example, that the memory allocation in case of fixed partitioning techniques is having some blocks of fixed sizes, like let us say 2 MB, 4 MB and 8 MB sizes, and the operating system is going to use this we can say memory for, let us say, for a process which is having a requirement of 3 MB. Now this 3 MB process, if given a 4 MB block, will result in the wastage of 1 MB of this random access memory. So this internal fragmentation, here you can see on the screen, we have kind of two scenarios in which we have one 4 MB block and some other blocks of 4 MB, 2 MB and 8 MB, and now there is a process P1 which is looking for a block of 3 MB, and with any strategy, let us say the first fit or the best fit, one 4 MB block is being allocated to that process P1. So what is happening? Within that 4 MB, if you can see on the figure right side, the process P1 has taken its part, whatever is required, exactly 3 MB to be precise, and 1 MB is now left over. Now this 1 MB here is an internal fragment, and this is what you call internal fragmentation. So the process P1 with a size of 3 MB is given a block of 4 MB, and as a result 1 MB of free space is unused and cannot be used to be allocated to memory to another process, and hence the whole kind of idea or the whole system is suffering with internal fragmentation here. Now the problem of internal fragmentation is arising because of the fixed sizes of the memory blocks, and it can be solved by assigning space to the process via dynamic partitioning, which says that the dynamic partitioning is going to allocate only the amount of space requested by the process, and hence as a result there is no internal fragmentation. So yes, we can say the solution to the problem of internal fragmentation is dynamic partitioning. That means allocate the amount of space requested by the process, or allocate the that amount of process which is being requested by the process, and vanish with the concept of fixed size of the memory blocks. There is no fixed size block. If a process comes up and it is looking for a 3 MB block, 3 MB block is being given to that. Another process which is coming and asking for, let us say, 5 MB block, give that process the 5 MB thing, and hence we will be able to get rid of the internal fragmentation. Now coming to the other part of, or other type of this fragmentation, is the external fragmentation. Now this external fragmentation is something, or it happens when a dynamic memory allocation, it happens with the dynamic memory allocation, and the dynamic memory allocation was the solution to the internal fragmentation, that is fine, but in case of external fragmentation, that happens when a dynamic memory allocation method allocates some memory but leaves a small amount of memory unusable, and the quantity of available memory is substantially reduced if there is too much external fragmentation. That means many fragments have been created, there is enough memory space to complete some particular request or at least one particular request, but that is not continuous, and this is known as external fragmentation. So in order to have an idea of this external fragmentation, let us take a look at the figure. We have two assigned spaces here. One is at the bottom of the figure, but that is also leaving a space of 10 KB left. Another is assigned space is also leaving another chunk of 10 KB of memory. and in the upper part of the memory we have 30 KB left. So, if we can see the unused space which is not assigned particularly here is 30 KB plus 10 KB plus 10 KB, which makes a total of 50 KB, but please remember that this 50 KB is scattered, it is not in at a continuous position. And let us say we have another process which is looking for a 45 KB memory space. Ideally we have that space that should be allocated, that must be allocated, but because of the availability of the space in non-continuous fragments or in terms of external fragments, we are not able to allocate this process 5 a memory of 45 KB, which is essentially available with the system. So, this is what you called external fragmentation. Internal fragmentation we have seen that comes with the we can say fixed side of partitions, and the idea to get rid of internal fragmentation is just to remove the constraint of fixed side partition and allocate the memory on the basis of dynamic allocation, as and when which particular process needs what amount of memory, that is being allocated to that. But that also gives us the problem of this external fragmentation. Now, why this problem is occurring? Because the random access memory is being allocated to the process in a continuous manner, and it is done in two of the techniques, paging and segmentation, which we will be covering in our upcoming lectures, where memory is allocated to the process non-continuous. So, if we are going to allocate the process continuously, it is going to give rise to the situation of external fragmentation. But if we can say that we are going to take away this condition of continuous memory allocation, external fragmentation may be decreased. But can we do something in order to reduce this external fragmentation, that too with we can say the continuous memory allocation? So, yes, there are techniques which comes as the solutions of this external fragmentation, and these techniques are compaction and the defragmentation. So, compaction basically is one method which is used for removing external fragmentation. Compaction, as you know, is compacting the requirement of the memory. External fragmentation may be decreased when dynamic partitioning is used for memory allocation by combining all the free memory into single large block. So, in utilities, in disk utilities, you have also kind of noticed one utility which is of disk defragmenter. So, this defragmenter is the utility in which it is going to take all the kind of non-allocated chunks or non-allocated fragments of the memory, and they are being clubbed or merged together. The large memory block which is used to allocate the space based on the requirements of the new processes, that can be created by the process of defragmentation. So, either we kind of compact the requirement or the memory requirement of the process, or memory required by the process can be compacted. One is this solution which is named as compaction. Another solution is whatever fragments are available at scattered locations, you need to merge them. That means that fragmentation has to be taken away with the help of defragmentation, and for this we have a utility available which is known as disk defragmenter. Now, coming to, we have this process of fragmentation. There are some advantages and disadvantages of this process of fragmentation. So, the first advantage here is the faster data writes. So, the data writes in the system which is having some fragmentation may be faster then the reorganizing data storage to enable continuous data writes. So, if we want to have continuous data writes, we need to organize or reorganize the data storage, and if we are ready to live with this fragmentation, we can have faster data writes. That is one of the we can say advantage of the fragmentation thing. Another one is it will also result in fewer failures. That means if there is insufficient sequential space in the system that does not support fragmentation, the write will fail, and if the fragmentation is being supported, it is not going to kind of have a failure. And another thing with the fragmentation is the storage optimization. Now the question comes up, how can the storage be optimized, or storage optimization can be an advantage of the fragmentation? That we can see here. A fragmented system might potentially make better use of a storage device by utilizing all or every available storage block. So here is also an kind of other side of the coin, which is the advantages. Coming to the disadvantages, there can be disadvantages of the fragmentation thing. One is need for regular defragmentation. That means that utility has to be kind of we can say run on the regular basis if we want to have a continuous allocation, or if we want to have defragmentation. The more fragmented storage device performance will degrade with the time. So the more fragmented storage devices, the performance will degrade, because it will kind of increase the requirement for operations like defragmentation and so on. And another disadvantage is the slower read times. That means the time it takes to read a non-sequential file might increase as the storage device becomes more fragmented. So in this lecture we have seen the process of fragmentation, and before looking into the fragmentation, we have also covered the two allocation strategies, which are best fit and the worst fit. After that, we have covered fragmentation along with its advantages, disadvantages, its type, and the fundamental idea that what actually fragmentation is. This is what we have all covered in this lecture. Hope you have enjoyed it. Here is a list of references which is being used for the preparation of lecture. I will see you in the next lecture. Till then, please take care. Goodbye.